All right, so let's dial in. I may have exaggerated a little bit about the hardest lesson. Certainly, I would say some people find specific parts of working with entities to be the hardest thing to do. Other parts are not so bad. In fact, I would argue people enjoy them. But there are some aspects that are can be challenging. So we need to lock in. Of course, you guys are all locked in all the time, but let's especially lock in today. To begin, little motivation, I have two functions that I'd like you guys to graph using skills from the last week or so. So I'm asking you to graph, and it's not a complicated graph. I'm asking you to graph the negative of the sine function. Dashed in red here, apologies for my colorblind people, I've graphed the basic sine function. So what would the graph of negative sine x looks like? And then list its properties. And then I've graphed the basic cosine function here. Can you guys graph what cosine x plus 90 would look like? So I'll wait a sec while you guys make those two graphs, and we'll see what shakes down. All right, what does the graph of negative sine x look like? Its amplitude, that negative is like -1. Its amplitude is still 1. But I'm just going to add in brackets here. We know that it's flipped, right? Or like reflected in the x-axis is the fancy way. Why is my face so big? I mean, why is the screen capture of my face so big, I should say? What's the axis? Well, the axis is just 0, and it looks like there's no phase shift. And the period, nothing is multiplied by the x. The period is still 360. So all we really need to do to sketch the graph of negative sine x is from our starting point, just go down and come back up, and go up and come back down. Poor choice for my starting point label. Let's move it. Let's use black. I'll put SP down there. Let's keep using pink. There. All right, there's the graph of minus sine x. So what, Mr. Smith? What does this have to do with anything? We did this several days ago. Can you guys graph the cosine of x plus 90 degrees? You may notice something about those graphs. Here I come. I cannot contain my excitement. I have to come along for the ride with you guys. The only thing different with B for the all the properties, it's a phase shift left 90. So instead of starting, because it's a cosine function, instead of starting with the maximum at 0, 1, it's going to be shifted left 90. So I'll put a starting point there. Max there and there. Take it in. Take it all in. What do you guys notice anything about those two graphs? They are the exact same graph. They are not just similar and they share a few properties. Those two graphs are the same in every way. They are the exact same graph. I don't know why I have so much space to write this. They are I'm going to put it in caps, the exact same graph. Now, what's interesting is you guys here have actually proven your first trigonometric identity. I haven't told you guys what an identity is yet, but you've actually proved one here kind of graphically. You guys have shown, it turns out, that the cosine of x plus 90 degrees is equal to the negative of sine x. This is true all the time. For all values of x, it doesn't matter. Now, can you guys humor me? I have space here, so I'm going to jot this down. We're just kind of improvising here and freestyling a little bit. Can you guys let's look at what happens when, say, x equals, let's use 16, hashtag Mitch Marner, new dad, game-winning goal. What happens when x is 16? Can you guys evaluate the cosine of 16 plus 90? I can do that. That'd be 106 degrees. Can you guys slam that in there? And then can you guys also do the negative of sine 16 degrees and see what you get? Cosine 106. Cosine 106. Negative 0.276, let's say. And then sine 16, but make it negative. Would you look at that? Negative 0.276. Do you guys do the same thing? That's going to happen no matter what we plug in. So, no problem.
I am grabbing canoe to student services.
Sure.
Thank you.
This is going to happen all period, isn't it? We've got to go to see it.
Thank you.
Now, you guys, for you people, you don't need to jot this down, okay? In your grade 9 course, you guys solved like little linear equations. I know this is a very simple linear equation, but that equation has one solution, right? What value of x makes that equation true? You guys can just flash me a gang symbol or something. X equals 4. That equation has one solution. And then in your grade 10 course, you guys did work with like quadratic functions. And we reviewed a lot in this course as well. Here's an equation that has two solutions, two values that make that equation true. X equals 1 and x equals 3 satisfy that equation. This equation here has infinitely many solutions. X equals anything solves this equation. Plug in 16, solves the equation. Plug in negative 5.4, solves the equation. Plug in root 2, solves the equation. This is an equation that is true all the time. We give those things a special name. Equations that are true for all values of x are called identities. So this was your first trig identity that you've shown is true. So let's jot that down. Identities. I was going to write on my tablet with marker. Identities. Equations that are true for all values of x. We'll keep it simple. We'll just say all values of x instead of all values of the independent variable. So today we're looking at more trig identities. Some are very, very useful for your later math courses. So we have one and we showed it visually. All right, are you guys clear on what an identity is? An equation that's true for all values. Are you guys convinced this one's an identity? The left and right side gave us the same graph, right? Okay. Let's continue that. We're going to investigate another identity. So now I've actually scaled this down. So we can use exact values for the first 4. For the remaining ones, I think there's just 2 more remaining ones. Now, let's dive in here. Now, this is some new tech for you guys, some new notation. Up to this point in your math careers, you guys have not seen the sine squared of an angle. Let me tell you what that means right now. All that means is, I'm going to rewrite it this way. This just means you're taking the sine of 0 degrees, and then you're going to square it, and you're going to do the cosine of 0 degrees, and you're going to square that. For this question, you can use your calculator or you can use a unit circle or what have you. I think most of you guys have your calculator handy. So why don't you just slam those in there? Sine of 0, I believe, is 0. And the cosine of 0, I believe, is 1. 0 squared plus 1 squared is equal to 1. So the sine squared of 0 degrees plus the cosine squared of 0 degrees is equal to 1. Are you guys convinced equal to 1? Can you guys use your calculators and do sine squared 90 plus cos squared 90? And then if you can, use exact values for the next two. You might need your special triangles if you have them somewhere. I'm going to quickly check on our 3Ms, pause the video, and then I might do the next two with you. All right, 3U people. Now, I'm going to rewrite this one more time, that the sine squared of 90 is just sine 90 squared. And then the cosine of 90 is cosine squared 90 is cosine 90 squared. And after that, I'll just assume we understand the notation. But that is 1 squared plus 0 squared. Did you guys get 1 as well for that one? Interesting, interesting. How about sine squared 45 plus cos squared 45? So from our special triangles, which I've had you guys draw several times, the sine of 45 is equal to 1 over root 2. The cosine of 45 is also 1 over root 2. Look what happens when you square these and add them together. 1 over root 2 squared. Well, when you square 1, you get 1. And when you square root 2, you get 2. Do it again. Guys, what's 1/2 plus 1/2? It's equal to 1. Very cool. So far, we've got 1 every time. But we're working with some special angles here. Maybe it's only true for special angles. Let's try the next one. The sine of 30. I always have to think about this in my head. Is sine 30 the one that's 0.5 or is cosine 30? Sine 30 is exactly 1/2. The cosine of 30 from our special triangles is root 3 over 2. What happens when you square these and add them together? 1 squared is 1, 2 squared is 4. The root of 3 squared is 3, 2 squared is 4. And what's 1 fourth plus 3 fourths? It's 4 fourths. Those add to 1 as well. If you're not convinced that the sine squared of an angle and the cos squared of an angle added together give you 1, try it with 123 degrees, which seems to be a fairly random number. Now I will just throw in the decimal values here. The sine of 123 to 3 decimal places is 0.839, and we'll square that. And then the cosine of 123 is equal to the negative of 0.545. If you square those two numbers and add them together, you should get very close to 1, because I rounded a bit. So it might not be exactly 1. Let's try it. 0.839 squared plus negative 0.545 squared. 1.000946. I did some rounding. You're getting signed out? Okay. It's basically 1. If you're still not convinced, pick your favorite number and do the sine squared plus cosine squared of your favorite number. Now, if you're lame, then you can just do the one I'm doing. I'm going to pick 34 for Austin Matthews. It looks like this should give me 1. Cosine of 34, 0.829. You guys should be picking your own number, or at the very least, verifying this one with me. 0.999722. I got 1. It appears that the following is true. It appears that if you take the sine squared of an angle and the cosine squared of an angle, it appears that you get 1 all the time. We just kind of did 6 values and we got 1 all the time. Are you guys convinced? It appears this is true all the time. This is a pretty neat looking identity. Now, we couldn't do this one with graphing because you guys haven't, at this point in your math careers, learned how to graph the square of a function or to graph the sum of 2 functions. But numerically, it certainly seems like this one is true. This identity is so useful, it has its own name. And because it kind of looks like the Pythagorean theorem, we call this one, shockingly, the Pythagorean identity. It rolls off the tongue. This is the Pythagorean identity. Now, I'm going to give you guys the 3 identities or kind of groups of identities that you guys are expected to come out of grade 11 with. So let's dial in. Here are the 3 identities you absolutely must know coming out of grade 11. The first we just saw. I'm going to recopy it down. Sine squared x plus cosine squared x is equal to 1. And we now know what that notation means. It means the sine of an angle squared plus the cosine of an angle squared is equal to 1. Now, this can also be rewritten in 2 different forms, depending on what you rearrange for. So I'm going to put a little or here. If you rearrange this for sine x, you could say sine squared x equals 1 minus cosine squared x. Or if you rearrange that first equation for cosine squared is 1 minus sine squared x. Those are not different identities. It's the same identity, just rearranged. Okay? That's one identity, the Pythagorean one. We're going to show it's true in a second. That's the probably the single most important one. The second identity is called the quotient identity, and it looks like this. It turns out that the tangent of an angle is equivalent to the sine of the angle divided by the cosine of the angle. I'm going to show you guys why both of these are true in a second. The third, you guys actually know these already. We've actually talked about them. So the reciprocal identities. We learned about these last week or early this week. I've lost track. The cosecant of an angle is the reciprocal of sine. It's 1 divided by sine. We learned this in our lesson on the reciprocal identities or the reciprocal ratios. The secant ratio is 1 over cosine. It's the reciprocal of cosine. And then we had one more ratio. The reciprocal ratio cotangent x is 1 over tan x. If you guys can add one more little equal sign there, though. If tangent is sine over cosine, that means cotangent you can write as cosine x divided by sine x. These are the identities you need to come out of grade 11 with, and that we're going to play around with today. We've already illustrated that the Pythagorean identity is true. I'm going to prove it to you guys in a second. I will show you guys that the tangent, that quotient identity is true. And then the final ones we've already seen before. Okay, so let's show the Pythagorean identity is true. And actually, it doesn't take a lot of work. Check this out, guys. Here's a right angle triangle I stole from the internet. What does the Pythagorean theorem say about this triangle? Well, the Pythagorean theorem says that c squared, I might write this differently, a squared plus b squared equals c squared. That's drilled into you guys. But in terms of a right angle triangle, this is like saying the opposite squared, I'm going to put OPP, plus the adjacent squared is equal to the hypotenuse squared. What I'm going to do next, check this out. I'm going to divide every single term here by the same thing. I'm going to divide by the hypotenuse squared. Divide by the hypotenuse squared. divided by the hypotenuse squared. Guys, which ratio is opposite divided by hypotenuse? It's the sine ratio. Which ratio is adjacent divided by hypotenuse? It's the cosine ratio. And what's anything divided by itself? It's equal to 1. So there you go, guys. We've proved the Pythagorean identity just like that. I'll use theta, because that's just in my diagram here, plus cos squared theta is equal to 1. Boom. Big check mark. It's not that hard to prove. Very cool. And that's also kind of why it's called the Pythagorean identity. The next one, because I didn't want to make your note too big, and I didn't mention this earlier, I apologize. I think I had an extra blank page at the end of my document. When I printed it off, it gave you guys an extra blank page. So you can just use that as, I think it did. Did it? Yeah, sorry about that. My apologies. Can you guys check this out? You can feel free to copy this down in the margins or not. I'm not your dad. But check out the following. Would you guys agree that tangent is opposite over adjacent? Well, I'm going to do something to the top and the bottom to keep this expression the same. I'm going to take the top, and I'm going to take the top and divide it by hypotenuse. And I'm going to take the bottom and divide it by hypotenuse. These are equal because they do the same thing at the top and bottom. Well, what's opposite divided by hypotenuse? Well, that ratio is the sine ratio. And adjacent over hypotenuse is simply the cosine ratio. This is the quotient identity that we have in the front. It's very easy to show too. Okay? The tangent, you can always write tan of an angle as the sine divided by the cosine. Very cool. I just didn't want to make your note too long. But I did anyway because I added an extra piece of paper on. All right. So let me zoom back in here. These are the 3 identities you guys need to have in your back pocket, ready to pull out at any time. You just know this is true, and these are true. Part of the grade 11 course is to prove even more trig identities using combinations of these basic identities and skills we've developed over the course of our math careers. Some of those skills we even just learned in this course. So let's prove some more identities together. Was that the announcements again? Oh, I just saw people look up, but they're just watching the time because they're bored. I won't take offense. I might go home and cry to a pillow later, but for now, I'll maintain my composure. Let's continue. Guys, check this out. Let's prove this identity is true. It turns out if you take the sine of an angle, the cosine, the tan, the cosecant, secant, well, that should be cotangent. I apologize. That should be cotangent, fairly important. If you multiply all 6 ratios together for any angle, you get 1. Let's prove this is true. Now, to prove an identity is true, you have to somehow show that both sides are equal. So we're going to show here that the left side is equal to the right side. So I'm going to show it this way. I'm going to manage my space well, so Ms. Plattner's proud of me. I'm going to write down LS for left-hand side. We're going to take left-hand side and work with it. The left-hand side is sine theta times cosine theta. But you guys have an identity that helps you write tangent in terms of... No problem. Yes.
Thank you.
Actually, let's do it this way. So I mentioned earlier, I'm going to pause the video. You guys have our reciprocal ratios. Instead of saying sine, cos, tan, cosecant, secant, tan, let's replace sine, or let's replace cosecant with what it's equal to. Cosecant is the reciprocal of sine, 1 over sine theta. secant is the reciprocal of cosine, 1 over cosine theta. And tangent, or cotangent, is the reciprocal of tan. It's 1 over tan theta. And now we just use algebra skills from our earlier grades. Look, sine theta over sine theta, cosine squared theta over cosine squared theta, tangent over tangent, all of those things divide by 1, or divide to 1. I'm just going to illustrate this by just dividing all those out. They all divide to 1. And what you're left with is equal to 1. And this is equal to the right-hand side. We have proven, put a little check here, we have shown that the left-hand side of this identity is equal to the right-hand side of it. We prove this identity is true by using our reciprocal ratios. That's one way. If you guys see an identity that has your cosecant, secant, and cotangent in it, one strategy for showing it's true is to see what happens if you replace those reciprocal ones with what they're equal to. Sometimes some nice things fall out like this one. All right, let's do a second example together, and then we'll take some questions. All right, we're going to prove that 1 minus the cosine squared of an angle is equal to the product of the sine, cosine, and tan. Now, this one is not immediately clear on a strategy for us to show this is true. But one thing you can always do, if you guys see a tangent, you guys can, one useful strategy is to write it as sine over cosine. So I'm going to manage my space this way. And over here, I'm going to say right side equals to sine theta times cosine theta. And you guys now know that tangent is sine over cosine. Now, does any neat cancellations happen here where we can simplify this? Well, one thing does. We have cosine over cosine. Those divide to 1. And what we're left with on the right-hand side is sine theta times sine theta, sine squared theta. When you guys see sine squared or cosine squared, that's a clue that maybe you can reach for that Pythagorean identity. Can you guys flip on the front? Is there a way we can connect the right-hand side? The front, excuse me, I meant the previous page. Is there a way we can connect sine squared theta with what's on the left side, 1 minus cosine squared theta? Is there a relationship between sine squared theta and 1 minus cosine squared theta? What is the relationship between sine squared theta and 1 minus cosine squared theta? They are exactly equal to each other. We have actually proven this identity is true. Sine squared theta, using the Pythagorean identity, is 1 minus cosine squared theta. And this is equal to the left-hand side. We did it. This time, we started with the right-hand side and made it look like the left-hand side. Now, for the purposes of you guys going back and studying later, I'm just going to add a little note here. We use the quotient identity at that step, and then we use the Pythagorean identity, I'll just say Pyth at that step. So those two examples illustrated some basic strategies. Write things in terms of sine and cosine, or their reciprocals. Or if you see a ratio is squared, possibly use the Pythagorean identity. All right, look at us. We've ramped things up in a big way. You guys don't even know what the graph of tan theta looks like. So how do we show this one by graphing? But using our basics, we can do it. All right, we got those two basic strategies. Let's ramp things up. Oh boy. Sine theta over 1 plus cosine theta is equal to 1 minus cos theta over sine theta. That one looks a bit intimidating at the start. And if I look for any those basic tips, rewriting things in terms of sine and cosine, there is no tan, there is no cosecant, secant, or cotangent. It's already in terms of sine and cosine. And also, there's no squared things right now so that I can use my Pythagorean identity. I'm gonna give you guys a little trick there. There is nothing wrong with manipulating an expression before beginning. This is a proportion, right? One thing over another equals one thing over another. You guys have tons of experience with the sine law, etc., working with proportions. Let's use some cross multiplication here and see what shakes out. I'm actually just going to make a note. We're going to use cross multiplication. Little crisscross applesauce. So what do we get? When you multiply sine theta times sine theta, you get sine squared theta. On the right-hand side, when you multiply 1 plus cos theta times 1 minus cosine theta, well, that's just equal to 1 plus cos theta times 1 minus cos theta. But now we have a bit of direction. You guys have a binomial times a binomial on this right-hand side. Let's start with the right-hand side now. We've rewritten our identity in a different way. Can you guys take that right-hand side, which I'm just going to rewrite as 1 plus cosine theta, 1 minus cosine theta, and can you guys use your distributive law, 4 multiplications to multiply this out? What do you get? You guys do that. I'm going to pause the video. I'm going to check in on see if there's any 3M questions. All right, here I come along for the ride. Check this out. 1 times 1 is 1. 1 times minus cosine theta minus cosine theta. Guys, let's dial in. Remember my little rant from a few minutes ago. Cosine theta times 1 is cosine theta, and cosine theta times minus cosine theta, it's minus, and cosine squared times cosine squared theta. Look what happens. Negative cosine theta and cosine theta add to 0. And you're left with 1 minus cosine squared theta. I wonder what 1 minus cosine squared theta is equal to. I see squareds. I think Pythagorean identity. What is 1 minus cosine squared theta equal to? It's equal to sine squared theta. That's literally the Pythagorean identity, which is our left-hand side. We did it. We showed the left-hand side and the right-hand side are equal. This identity, our original identity, was true for all values of theta. We did it by turning this messy-looking one into something that was a bit more manageable to work with. We could use our algebra skills to show. Not too bad from this point, in my opinion. All right. Anything you guys want to chat about? Otherwise, we're going to do one more, and then you guys will do a second one. All right. Let's look at our next one. All right. I see squared ratios here, so I'm getting excited. I'm like, maybe I can use my Pythagorean identity. Guys, does tan and secant appear in either versions of our Pythagorean identity? No. So we can't reach for that just yet. What we can do is try our basic strategy. Let's write everything here in terms of sine and cosine. Can you guys do this with me? And specifically, I think we'll start with the left-hand side here. It looks like it's the most involved. Tan of theta is equal to sine of theta over cosine theta. So can you guys do this with me? We can rewrite the left side as sine squared theta over cosine squared theta plus 1. We have 2 rational expressions. It would sure be nice if some handsome guy with a buttery voice taught you how to do this earlier in the semester. That would be me. I have shown you guys how to add rational expressions together. You just find a common denominator. This one's not too bad. We just need to write 1 as a fraction over cosine squared theta. That's not too bad for everybody in this classroom. 1 is just cosine squared divided by cosine squared. You just get a common denominator here. I'll just write this down. Common denominator. I'll even write it all out. Denominator. Like, guys, we're literally done. We can now add these two together because they have a common denominator. I'm going to combine them first. I think some of you guys might even see where this is going. What are we left with? On the top, we have sine squared theta plus cosine squared theta. On the bottom, we have cosine squared theta. What does sine squared theta plus cosine squared theta equal to? No. 1. Oh, okay. I thought you said cosine squared theta. 1. That's from our Pythagorean identity, right? And wouldn't you know it, 1 over cosine theta, is that not the very definition of secant theta? 1 over cosine squared theta is equal to secant squared theta. That is the very right-hand side we were looking for. Guys, we did it. No problem.
I have Claire. Do you see services?
Claire left. She's not here right now.
Okay, thank you.
Sorry. She's going to page me right now, yeah. All right. Guys, everything there was manageable. You can all do that. We rewrote tangent as sine over cosine and used algebra skills we already have in theory. Can you guys try the next one? It's literally the same question, but with some different ratios. Take the left-hand side and write cotan. I'm even going to help you guys out. That's the kind of guy I am. Cotan, we know, is equal to, we're going to start with the left-hand side, is cos squared theta over sine squared theta. Can you guys repeat the process that we just did? Find a common denominator. Mash them together. See what shakes out. I'm going to let you guys get to it. Yes. Yeah, sorry. Well, sometimes when students say they're signing out, they don't actually sign out. Just as like my experiences as a teacher. Believe it or not, teenagers, don't always tell the truth. But sometimes the office people don't communicate with each other too, so that's probably it. I'm going to play catch up. How do we add rational expressions together? By finding a common denominator. You can write 1 as sine squared theta over sine squared theta. We can now add these together because they have a common denominator. Here the denominator is sine squared theta. Sine squared plus cosine squared is equal to 1. And the reciprocal of sine is cosecant. We did it. Yay us. I'm going to zoom out a bit, take those both in. They're literally the same problem with the exact same kind of properties that we use. You guys did it. We exposed you guys to identities. You lived to tell the tale. I can tell you, I did use trig identities in my master's research project. I was still using them 7 years into my postgraduate studies. They are useful. This is where they're introduced to you guys in your grade 11 course. Because think about what we did today. We did graphing. We did reciprocal ratios. We tied it all together. A lot of the stuff from this unit. All right. I'm going to give you guys some practice. It's really important that you try as much as you can. I have full solutions to this practice that I'll link in the newsfeed so you guys can check stuff tonight. And before I stop talking, ChatGPT does a great job proving trig identities. If you're at home, you don't want to look at my solutions for whatever reason, Photomath, ChatGPT, they can do these no problem. It's not cheating when you're studying and trying to learn how to do stuff. Let's get a few done while we're in class. You got it in before you had to go. Try some things tonight. I'll post solutions in the newsfeed, okay?
Here you go.